very happy to see you here. This is the last presentation of the last day of this excellent event. And it's good that we still have people in the room. Thank you for staying. Okay, you are welcome to join this community, and please scan the QR code if you haven't done so yet. My presentation is called Service Architecture, Reducing Labor Costs and Improving the Security Level. First, a few words about myself. I'm Yuri Kardikov, and I'm with eCassier company, and I'm head of Identity and Open API. And I'm a product owner of an identity platform that ensures quite a number of important functions. A few links to the articles that I published in Banking Review, Bankovskoye обозрение. One is about protecting API, and the second one is why banks would want to connect to open APIs. So what the presentation is about. First, it's about architecture. There will be two components in my presentation, two parts. First is architecture of UI services, and the second one is architecture of system to system. So what's in common, what's different, and how you can use the strengths of each of these. And secondly, how to implement safe authentication of users without libraries and without writing a single line of code. So that's everybody's dream, how to get everything doing nothing. It is possible, but still probably you'll have to write just one line of code. Second, the issue of secure information storage, how you do that securely and how you never give this information to the front office. The front office is, the front end is not a trusted environment, so how to avoid giving information there. And finally, opening ports on a firewall, that's a real headache for security. When a service is closed but ports remain open and they represent a vulnerability, there is a solution how to radically avoid that. You can open access to a service without opening a single port. Summarizing, using two components, API gateway and secure authentication, how to build a safe and secure infrastructure and to save company money. So here's OWASP top 10. Broken access control is #1 vulnerability, and #7 is identification and authentication. So you can see that it's a very practical topic. Okay, let's start with an introduction. Let's get to know the components of the process. Before claim-based authentication, we only had two parties to the process. That's the user and the service. And for authentication to happen, the user sends their credential to the service, a login and a password. So with every authentication, the user sends their credentials to the server. Why this architectural approach is a bad one? Every service gets a user's secret. So if the user has just one password, or the passwords are very similar and just one character is different, then if this service is hacked, the user's password is compromised, and administrators have access to this information. If you turn on logging, then this information would be accumulated in logs. And I saw that is one of the banks, which is a top 30 Russian bank, where when there was a change of a login or password, that was recorded in logs, and essentially the administrator could get access to secret information of all the users. And in test environments or QA environments, there's the debug mode that logs a lot of information, and there's a potential for leaks. I want to mention separately a Pomula template, which is essentially an anti-secure template, because it encourages the user, rather than storing their secrets, to unveil their secrets. But still, that is a security template, quite widespread one. To address this, we need a third participant, which is an authentication server. So rather than going to the server, the user goes to the authentication server, and their login and password would be stored there. And the service would issue a mandate. The mandate states that such and such name, such and such privileges, etc. Having received this mandate, this token, the user would present this token to the service. And because the service trusts the authentication server, it validates it first, and then if it's okay, then it lets the user in. This sounds difficult, but in real life we're all used to that, because our passport is an example of a claim-based authentication. Okay, so let's take the government. We go to a government authority. We get authenticated and we receive a password. The password says that our name is such and such, we live in a particular place, and our date of birth is such and such. And we then use this password when we go to services such as a bank or a government services center. And because the services trust the government, this trust arrow must be there, then this is sufficient documents for authentication. And the same happens digitally, where the place of the government is taken by the authentication server, and the place of the password is taken by an access token. By presenting this token to the server, we submit a certain mandate without a login and password. And let's then go to the next element, which is the structure of services. We have a UI on the left and we have a service on the right. And to get the API that this service provides, the UI makes a request, and it adds to the request body under the header authorization the access token. So how do we add the authentication service in this structure? So there are two logical implementations. Either the service takes up this task. If a request is unauthenticated, it would send the user to get the authentication. Or the second implementation, the service could say that it would return status code 401, and the user decide themselves how to get this access token. And we can stop a little bit here, because what this leads to is that people start getting ideas. Okay, I read an article on Harbor and I have a library, and this leads to a situation which is described in OWASP. Because this approach leads to vulnerabilities. So let's think what happens here. The service is up and running, it carries out some business functions, and it doesn't want to do authentication. Imagine you go to a government services center without a password. You don't get an explanation of what you have to do to get a password. It's up to you to do that. That's point one. Point two, or giving it to the UI side is an even worse thing, because UI is by default not a trusted party. So by default, keeping any secrets there, keeping it anywhere else than the service, it's not a bad thing. So what happens, what this leads to is the search for libraries. There are many articles, many libraries that help address this, but the problem is that developers are not experts in authentication protocols. This in itself is quite a big domain of knowledge, and just by following configuration guides, it is very easy to pick the wrong library or to pick the right library but the wrong mode, simply because you don't have enough knowledge, your attempts are not always successful. And developers, instead of developing the feature set that the business partners expect, the customers expect, they spend the time on infrastructural tasks. Authentication is an infrastructural task. So if you started thinking about it, you might come up to a conclusion that neither the service nor the front end want to do that because it's not their core business. Essentially, we know that no one likes monolith, and here you want to add an authentication task to a service. Essentially, you try to recreate a monolith solution. So what can be done here? A solution is available, and hence we add the fourth element to our diagram, which is API Gateway. That is the component that addresses all tasks that neither the UI nor the service want to address. This is quite a sophisticated diagram now, and I'll try to explain how it works. On the left, you have a UI that could be static, that could be a single-page application, a native app, a mobile app, doesn't matter. On the right, there's the service that provides the API. The UI would, as a first step, send a request to the service. The API gateway intercepts that, sees that the UI is not authenticated, and does the following. In accordance with its configuration, it develops a request, the address to which the UI should go to get the token. And at step 2, it returns a standard header 301 redirect to the address to which it should go to get the authentication. The UI follows this redirect, and by going to the service, the form of the API gateway of the authentication server is displayed. At step 4, authentication happens. Normally it's through login and password. Then there's the second authentication factor. It could be a phone number, it could be biometric. All the methods that are available on the server. And only at this step, the user discloses their secret information. The service, the API gateway don't have it. The secret information is only exchanged between the user and the authentication server. After that, we can give the access token to the UI. So at step 5, we can return the access token, but we don't do that because the UI is not a trusted environment. So instead of the access token, we send it a dummy that doesn't contain anything meaningful with 301 redirect, and in the location header, it is being sent to API gateway. So it goes to the API gateway and gets this surrogate authorization code. And then on its own, without the user browser, it exchanges the authorization code to the access token. So what this leads to is that there's no disclosure between, no information disclosure between the service and the user. And the sensitive information, the access token, does not go to the UI, it stays on the API gateway. So you can see that this is a standard authorization code flow used here. Okay, so we have gone through the next step. We have authenticated my unauthenticated request. What do we do next? Next, the API gateway saves that in the session storage. It uses encryption and it modifies the first incoming request. It adds to it the authorization header, the bare access token, By sending the request from the UI which is unauthenticated, it goes to the service with an authorization token. The service responds and it adds to it, the API gateway adds to it the session cookie. So with any subsequent request, the session cookie would be added to the request automatically. It's decrypted at the API gateway, and the API gateway finds the identifier which it can use to get information from the session storage. So having received this request, having decrypted the cookie and having gone to the session storage, it adds the access token, and this happens with every request. So with that, we send a surrogate to the UI, a session cookie, which is has nothing exciting in it. There are no access tokens that hackers might start studying, and the service gets the access token. So we ensure secure storage of sensitive information that doesn't leave the secure perimeter. In terms of storage, the API gateway stores access tokens, and temptation might arise that a rogue administrator or a hacker might leak the database and abuse the tokens. To avoid that, we use algorithms that in real life are used in a bank depository. If you have ever been in a bank depository, there's a concrete reinforced room with very thick doors, and to get there you need to have two keys. One key is with a physical security employee, and the other one is with operations. And only having presented two keys, having received the clearance from the physical security and the business part, you can get inside. And the same approach is used for safe storage. Data, tokens in our case, are encrypted using initial vector algorithm. And it works in the following way. There's a key that's in the API gateway, and potentially it can be stolen. So if a hacker hacks into the system, potentially they may steal that. But the other part, the initial vector, is in the session cookie. The session cookie is encrypted, and you cannot open it directly. But once it is presented, the API gateway would decrypt it, extract the initial vector, and by applying its encryption key, it can decrypt the saved data. The same two-key approach for safe storage of information. So let's see what benefits this solution brings. But for some reason, my clicker stopped working.
Ну, да, соответственно, плюсы, да?
Okay, so the benefits. Tokens don't leave the secure network. They are not available at the UI. No hackers, no users can see them. Second, we don't disclose the login and password to the service. That is a secret, and we share it only with the party that we trust, and that is the authentication server. Importantly, this arrangement is very transparent by establishing a system between UI and backend. The API plus authentication service, it fully addresses the authentication. There's no need to do authentication of the front or the back. So rather than working on infrastructural functions, coders can do whatever they are paid for, and that is implementing business features. And hence we have an unbound authentication system. And why? Say requirements changed and we want to implement a two-factor authentication. We don't need to do anything in the service. The only thing that we do is we implement changes in the authentication service. And will then speak about two issues. First, what do you do when a service token, access token expires? Unlike a password that is valid for more than a decade, the service, the access token has a very short life. The recommendation is somewhere between 10 and 60 minutes. So the solution is in the refresh token. That's a special token that has a longer life. So when the access token expires, you can use the refresh token to get the access token. That is true, and that is the reason why it exists. But it has a side effect, this refresh token. Using that, you essentially give a third party an opportunity to act on behalf of the user. What that means is that the user has authenticated and has gone offline. The access token has expired, but the software has a refresh token. And even though the user is not there, the software can use that to get another access token and take some actions as if on behalf of the user. And it's a metaphor that we could use is a power of attorney. When one person wants to delegate some action to another person, you go to a notary, you issue a power of attorney, and that other individual can take actions on your behalf. But in the digital world, this often happens without the user consent. Imagine you come to a bank, you want to withdraw some money from your account, and you do that, but without you knowing the teller has got a POA to draw money. So you go away, you are now offline, and she can withdraw money. And it's as bad as it sounds. And refresh tokens are sometimes used in an unsophisticated way. Clearly, you don't want to do that, and the problem of user security is now something which has come on the radar of regulatory authorities. Once you go on a website, you may see that you're being asked about your cookie policy. You have to give consent, whether you want to have some additional cookies or just mandatory cookies. So in online banking, the topic of consent is a very important topic, because no one wants to get in a situation when someone gets access to the user's accounts without their consent. They have gone offline, but the app can still check on their balances and other banking information for the next 90 days. So to avoid that, there has to be an open consent to receive this refresh token, and there must be a mechanism for canceling that refresh token. So using authentication codes for using the refresh token for access token is not a good problem formulation. There is a solution that helps update the access token without a refresh token. These are scenarios that are typical for UI. And one of such solutions is SSO, a single sign-on. Let's look at the diagram again. Okay, so first time around, your request is not authenticated. You go through the system, you get a token for 10 minutes, access token. In 10 minutes, the token expires. In 10 minutes, you get another request, and the API gateway sees that the token has expired. What's to be done? Nothing is done. It's just a renewal of the same mechanism. The user is sent to the authentication server. but because the user authenticated there only 10 minutes ago, the server would not ask the user to submit their credentials. It would just update the authentication token and send it to the API gateway. So from the user experience, the next query to the API is 0.2 to 0.5 milliseconds longer, and the user wouldn't notice that. So using this single sign-on, it is possible to update the authentication token without a refresh token. Or you can use an inter-session cookie, but perhaps that is beyond this presentation. And finally, one last implementation where perhaps you need a little bit of a programming. But how do you understand at the UI side who is that person in front of you? To greet that individual, to say hello Yuri, for example, or hello John. The API gateway provides an endpoint that is protected by a session cookie. The API gateway would go to the authentication server, would get the information about the user's avatar and the name. So having processed that, the UI can greet the individual. So we have discussed the UI scenarios. Let's now talk about the system-to-system architecture. It doesn't have a user in the loop, and there are two scenarios. First, when someone is developing their app and they go to their Yandex profile, they issue an APK and they use it in their code. They provide a service to the user, and the information about weather or maps, for example, they get from Yandex. That's one implementation. And the other implementation is when there's no UI. A backend talks to a backend. And a good example is banking. Say an operational day is over and you've got to exchange acceptance acts or reconciliations. Next, what is the difference in architecture between users and partners? As users, we always use UI, so there's always a person behind the UI screen. And with partners, there might be or there might not be a UI, a user. So users only interface with the UI. We provide them a convenient UI to interact with our system. In system-to-system interaction, a UI is never used. It's one system talking directly to another system. A user doesn't have any IT competences. They are a user of the service and they don't have to be IT literate. On the other hand, the partner has a high IT competence, and importantly, they have their own infrastructure, that is servers that can store secrets reliably. And based on that, one last conclusion that users can work with certificates, but it's difficult. It's difficult even for experts, but for ordinary users, it is inaccessible. But partners can use with certificates, and we'll use these differences as we continue with our discussion. So let's build a typical infrastructure, and then let's make 3 steps to improve it. A typical structure is that there's a partner who wants to address a service, and it goes through an authentication at the authentication server, and they receive the access token. And because we talk not to UI but to another system, we may skip replacing the access token with a surrogate, with a session cookie, on an assumption that this is a qualified partner who can keep secrets. Then the partner calls on the service. The access token contains a number of statements and has a digital signature. The partner then calls on the service. The service does validation. Here we have one service, and having received the access token, they look at the statement and see that the access token is for them.
If the partner gives the data to another service, the server starts looking at the access token, see that he is not the final user, says, sorry, we're not going to work with you. And now let's try to improve the scheme. First step is authentication. How can we authenticate in a secure way? What kind of methods are there? Login and password is the first one. The partner sends the login and password in an open text form. Second is a common secret or symmetrical algorithm, HMARC. Third is private and public key and certificate. The fourth one, authentication at MTLS. All these four things are described in RFC, and there is a good base. It was analyzed by specialists. There is also a very popular template, API key. I didn't find any description, but it's a popular method. I think you know it. You go to the API company, get a key from it, and each time you add API key. Which methods are secure? There are two criteria. First, whether the secret is transmitted openly, and secondly, whether you use PKI. Login and password are transmitted openly. It can be encrypted or not encrypted. Common secret and HMAC doesn't transmit secret in an open way. It's hashed, but the secret is common for two parties, and we do not use PKI, and it's a problem. In a month's time, the secret may become invalid. We cannot do that. We cannot do it fast without code writing. Public private key and certificate. Of course, it's secure because we use PKI infrastructure. We can say that in a month's time or in a year's time, we have to change the certificate. And MTLS PKI is secure for the same reason. So the third line is application level, the fourth line is transport level. APK is not different from login and password. It's almost the same, and it cannot automatically expire. So we authentify the customer, then the access token that we generated. What is the problem? The access token by default defines the person who presents it. If it is stolen, then the thief will be able to use that token in my name. For example, I have 1,000 rubles. I cannot counterfeit it, but if I give that $1,000 to somebody else, and if the other person steals it from me, he can go to shop and get the service. So the money is not closely linked to a person. Those who presents it gets the service. Same with the access token. Of course, we can use proof of possession or holder of the key. If you want to go to bank and get the money or give the money, so you have to show your passport. You have to be authenticated. Same with the access token. We link it to the transport certification of the partner. So I show you the TLS gateway here. At stage 1, the partner is authenticated at the transport level by MTLS. He asks for a certificate. The gateway gives information about certificates to headers, and the request goes to the authentication server, and it issues the access token with one change, with transport hash, because this is a fingerprint hash 256. The transport certificate gives us the hash function, and the hash function goes to the header. It goes to the partner, goes to the service. At step 4, goes through MTLS authentication. The header goes to the service validates it, and there is one more step, an additional step. It issues the hash function from the certificate in the header. It compares it to what the access token contains. If it was stolen, if somebody else presented it, then we are not going to work with that token. We upgraded access token. It's not a bearer token, it's a token with proof of possession. And finally, a non-disclosure of data. We give the token to the partner, but it has a number of things which are secret or not secret, but the service needs it for authentication. For example, the trust level is low, the partner may be offended, or business information, terminal 445. The information that is not secret, but the person wouldn't like to disclose it. What can he do? And location as well. What can we do? The first thing which comes to my mind, we need integrity and confidentiality. Let's encrypt. It works. But we have to save resources, save cost. Why wouldn't use encryption? Because encryption is resource heavy, resource consuming. Cryptography is used, encryption is used, but it takes time and money. Second, encrypted token is twice as big as non-encrypted, so it raises your traffic. Your traffic grows significantly. Point 3, the procedure of encryption. Signature means that you sign something with your open key, with your closed key, then publish an open key, so you do almost nothing, but anyone can check it. Anyone can do the validation. Encryption does the other way around. You must take an open key of the partner to whom you are going to present the encrypted data. If you encrypt the same data and send it to 10 partners, you need 10 different encryption procedures, of course. And the main thing is that to get encryption, you must use an open key, not of the partner who asks you, but of the service that will consume your data. And there is no engine for such kind of exchange. If we are in one organization, okay. If you know where the key is, you can send it to partner. But if it's the service of a different organization, Yandex, Vkontakte, and others, it wouldn't work. The service encrypts the token, but it cannot decrypt it because he will need the closed key, which it cannot obtain. So introspection endpoint and revocation endpoint are not possible in this case. Encryption is possible, but it raises security at the expense of speed and performance. The alternative exists. It is called reference access token. It's not self-contained. It's a reference token. For example, you can compare them. Reference is a string of 64 bytes. So it's a very small workload. JWS, it's 459 bytes. And encrypted JWE is more than 1,000 bytes. You can see the difference. The final architecture looks like this. Everything is the same as in the previous slide, but the access token is a reference token. It has some specific things. It is linked to a specific partner, to a holder. You can use it only after mutual authentication at a transport level, and the service gets just a string of 64 bytes. So there is one more task. We have to execute the introspection endpoint. The service goes to the authentication server and gets JSON with the same expressions as in the previous case. One more additional step, but it reduces network traffic, and we are not forced to transmit sensitive data. What are the benefits here? Secure authentication, PKI infrastructure, owner-related token. Only one person can use it, and reference token. We are not transmitting sensitive information because we transmit a surrogate or a replacement, and the customer is not required to understand the contents. He has to present it to the service. The service should understand it, we compare it, we reduce the cost. The services have a lot of tasks to do. They are all typical. Of course, they wouldn't like to do it, but we use the same scheme as before. There are API gateways, there are authentication servers, and it's not the service which does the job, but the API and the server, who validates, who checks everything, who revokes if necessary. So it's only part of API gateway does. So it's not done at a service level. We don't spend our money on that. The programmers will deal with business, and infrastructural work, routine work is done by the authentication server and API gateway. And the final point is how to provide access without opening network ports. The typical architecture is like this. On your left, partners and customers, then external firewall, then API gateway in the demilitarized zone for preliminary filtering. If it's okay, then it goes to services in the right network, and it is also protected by its internal firewall, and you have to open ports and close ports. And from time to time it becomes a problem, especially if you have a lot of services. There are a lot of holes and gaps there, and you have to monitor it. This is the solution. It calls reverse access. And this is the configuration. We have several API gateways, 2 in fact. One of them is in the DMZ, the other is inside the protected secure network. And the internal gateway initiates the connection to the DMZ API gateway. The connection is opened and is kept open. It's something like a pipeline. It can transmit oil, gas, or data, but it works all the time. Only when the query is validated, it gets to the internal API gateway along the existing yellow connection. You didn't open a single port at the external API gateway, but the service has been provided. You opened only one port at the internal API gateway. If a criminal gets into one of your services and you want to download the payload, he goes to the internet, but all the ports are closed and he wouldn't be able to get anything useful. Colleagues, at this point I would like to complete my presentation. This is my QR code. Please evaluate my presentation. It's the last one. I'm ready to answer your questions, please. Thank you. It was rather interesting. I have several questions. The first one, you said reference tokens. It is not signed. Why not signed? How not signed? If SSO gives you the token is signed to confirm to the gateway that it is his token. Yes, it was issued by this SSO. Please explain. Yes, we sign the token if it is self-contained, where we have 2 types of access tokens. Here, it's a self-contained token, which has all the expressions and the digital signature, and by having this token, the service can carry out validation and authentication if it gets the keys in advance. And it can do the job and do the authorization. If we change it, the reference token has no signature. It's just a string which is given to the partner. But at the authentication server, there is an information that this string is linked to a certain partner and to a digital certificate issued to that person. And what does the partner do? The partner sends this string in the header, carries out MTLS authentication at the gateway, and the service sends its request to introspection endpoint, where the verification takes place. It is not signed. Reference access token is not signed. So if we have API gateway, if 2 services interact, the partner service addresses us and presents access token. Our API gateway goes to the server and he gets the normal token. No, reference tokens are not exchanged for a self-contained. JSON is the answer. JSON expression. You cannot exchange reference token to self-contained token. It's not a token. It's just a JSON without a signature. At the introspection endpoint, it's not a token. It's a JSON with expressions which are not signed. Hi, thank you for the presentation. How well does your architecture scales with two gateway? Are two gateways a bottleneck? Let me put it this way. I cannot name the customer because we signed NDA with it. It's a large federal company with 16 million users. Most of the people present here use their mobile application. They use exactly this scenario and they have no bottlenecks. Moreover, API gateways are stateless. You can produce as many as you like. Of course, you have to keep them somewhere, store them somewhere. So it all depends on the database scalability. If the database is scalable, it's all right. We do not scale up our system. We just work as a microservice. We can add more and more. You have to scale up your database. Database scalability is the key. If it's a proprietary database, so you use appropriate mechanism. If it's NoSQL, so you use NoSQL tools. So it's the database that has to be scaled up. Thanks, I'm Alexander. I was curious at the very beginning because I saw authentication next to API gateway. I thought that it's wrong. Then I saw how it works, so you answered my first question. But I have one more. It's about open APIs that you mentioned. In the context of interaction with the customers, with internal development departments, QA, DevOps, do you practice API first, design first, or code first? How does it work? Look, so actually this is not the subject of my presentation. Of course, I would like to say that it's API first in our company. So we draw nice schemes and then codes are generated. But this is not exactly true. It is done this way, but not everywhere. In API gateways and server authentication, it's code first. And then automatically we draw the higher level pictures. Then analysts work. So it's the developers who are first now. In this particular case, yes, we tried to change it to make API first, but there are some technical difficulties. Thanks for the presentation. Did you think to try to pull internal gateway into the service to eliminate one point of failure? Good question, but into the service mesh, yes. We are thinking about it, we are working at it. Service mesh is a new technology, and our system was developed in 2015 when we did have such mesh. We are thinking about it, but there is no practical implementation yet. Thanks for the presentation. How applicable is this system if we try to implement it inside the protected network for microservices. For microservices, perhaps yes. We mainly have two options. One, we provide service to partners or to external customers. We have a scenario for internal authentication of bank employees. But in that case, most of the capabilities of the system becomes excessive, superfluous. For internal network, you can use the service mesh, and also when we send reference token to the introspection endpoint, how does the server understand that it receives that token from the service and not from a hacker? Well, good question, because it is not described in a single RFC. It's up to the vendor to decide. We do the following. To address the introspection endpoint, you need a certain scope. And in the authentication server, you have to identify all that. And the service is a client with minimum level of privileges and with limited scope. This architecture, is it used in commercial products? There is single sign-on there. Yes. Actually, talking about commercial company, our company is commercial. That's what we do. We offer such service. It's something like Keycloak, an analog of Congo. Thank you for the presentation. How do you authenticate if refresh tokens are refreshed automatically? If a criminal gets that token, do you trace activities of the user? The single sign-on technologies in the web, I don't know other methods. Maybe it's Cuckoo. After first authentication, you get a SSO Cuckoo. Of course, it can be tuned because you have a time limitation dictated by business. When the token expires after 10 minutes, perhaps, and session Cuckoo expires after 1 hour. For 10 minutes you work with the authentication token, you go to the server, we present Cuckoo, the server understands that you are still alive, and everything is transparent. Such scheme works, but you need to certain conditions that the expiration time of the token must be smaller than expiration time of the session. If it is impossible, there is another way. We can, at API gateway, to install your own session Cuckoo. And there are many mechanisms after that. You can use token exchange protocol to get token from API gateway, or you can issue tokens from API gateway. As such, you have a lot of mechanisms actually, but most often we used the following. The lifetime of token should be smaller than Cuckoo lifetime. Thank you very much.